Hello everyone, welcome to another video of our quantum computing course. In this video, I am going to discuss about qubits. So let us start the lecture with the very basic question, that is, what is a qubit? Okay. So if I give a very simple definition of this, then qubit is the fundamental, it is the fundamental unit of information. Okay, or you can say data. So fundamental unit of information in a quantum computer. Okay, so this is what is a qubit. So what is a qubit? It is the fundamental unit, okay, because we know that if we are having a computer, whether it is classical or quantum, we are going to process information. This is something I discussed in the previous lecture, that our main goal is to process information, right? Processing information, that means we are going to have a lot of data, right? So now processing means we are going to compute them. And for computing data are present in multiple formats, right? Data can be in the format of a number, it can be text format, right? Alphabetical characters can be there, or some special characters can be there, right? So all of this. Now these needs to be transformed to some other type of unit on which computations can be done, right? So that unit in case of quantum computer is qubit. Okay. Now, so to better understand this qubit, we can take the analogy of classical bits because we are comfortable with this, and also let us see what is the difference. Like why till today when we were using bits and everything was fine, then why we are shifting to qubits and what is so different? Like fundamentally, where is the major difference? And then because of the difference, what impact is getting created, right? And what power we are getting in case of quantum computers, that also we need to understand. So what happens is, for classical bits, we know that what it means. A bit means it is either 0 or it is 1. Okay, a bit can be either 0 or 1. So that means it is having two possible states. Okay, which means this 0 1 also, we call it sometimes on and off, depends which one we are taking as on, which one we are taking as off. So overall, two possible states are there, that is 0 or 1. Okay, so this is how our classical bits look like. Now what happens in quantum bits? Okay, so one more thing, just understand, we are calling qubits, right? So qubit is the short of quantum bits. So we take this qu from the word quantum and then add this suffix here, so this becomes qubits. Okay, so it is the short of quantum bits. So in quantum bits, what is there? Remember, in case of quantum okay, computer also, we are having two basis states, or you can say two fundamental states. Okay, and those two fundamental states are 0 and 1. Okay, so this sounds very similar. Here also in classical bits we are having 0 and 1, and in quantum also we have 0 and 1. These two are the basis states, or we can say fundamental state. Then what is the difference? The difference lies in that these qubits have multiple possible states. Okay, multiple possible states. Here what I have written, only two possible states are there. But in case of quantum bits, we can have multiple possible states. not just 0 and 1. 0 and 1 are the two fundamental states. Okay. But what happens actually is that we can combine this 0 and 1. We can combine 0 and 1 and make some other states. That is where fundamentally bits and qubits are different. Okay, so what did I say? That here in qubits, we can have multiple possible states, and this multiple states come by linear combination. Linear combination of the basis states. What are the basis states? I told you 0 and 1. So there is a way of representing this states. About states I will be discussing in the next lecture. There is going to be completely a separate lecture about quantum states. Okay, this will be my next lecture, but as of now I'm just mentioning it that here these possible states come by linear combination of the basis states. That means we are going to combine the 0 and 1 and we are going to get more states. Okay. So then that means what? Here what is happening? Here also we are using 0 and 1, but we are getting only two things, two combinations you can say, right? But here using 0 and 1, we are going to get multiple combinations. So that means that 0 and 1, you can consider these as your raw materials. Let us say you are considering these as raw materials. Now what is happening is you are using same raw material in both the cases. But in the previous one, in this case 1, you are getting less number of products. Less products, right? And what are the products here? The products are your states. Okay. So in case of classical, you are getting less number of products. Why? Only 2. But in case of quantum, we are using the same raw material, that is 0 and 1 only. But we are getting more products. More products. Okay. And more how many? So that is not a finite number, that is not an exact number. Many states we can get. So there is not one exact number for that. So now I hope you're understanding that why it is said quantum computers are very powerful. Definitely I will be also coming up with algorithms and through that we can understand that classical computers, some such problems are there which classical computer is not able to solve, but quantum can do it. Or maybe classical is able to solve, but quantum is able to do it more efficiently. So we use two terms actually very commonly known as quantum advantage and another one is quantum supremacy. So these are the two words that we use. Okay. Advantage, this word we use when, let us say, classical is also able to solve it, but quantum is able to do it more efficiently. Okay. So this is when more efficient task is happening. But we use the word quantum supremacy when quantum is able to solve something that classical is not able to solve. Okay. So I already told, but I'm just writing it. So quantum can solve, but not classical. But not classical. So I hope you're able to estimate at least that what is the power and what is the strength of this quantum computing and from where that strength is coming, from this fundamental difference. Here itself you can understand that how fundamentally we have shifted the entire way how we do the computation. Okay, furthermore many things are there that will be coming in upcoming lectures, but I guess through this you can understand that here itself the fundamental unit itself is changing, right? So that is what it is. So this is the difference between classical and quantum bits. Okay, so I hope this one is clear. Now, as I told that here linear combination is there. So how we perform that linear combination and how we write it, how we represent it, those everything is actually the part of the next lecture, which is quantum states. Each combination is a state. So how it is going to form, I will show you in the next lecture. Okay. One more analogy I will like to give here between these two is, let us say this is our Earth. Okay. Now we have the North Pole here and we have the South Pole here, right? Let us think about such a world where people can live only either at the North Pole or at the South Pole. Only these 2 points are allowed. No other. These are not valid regions to live. Okay, so if people are allowed to live only in the North Pole or in the South Pole, then that world is similar to the classical world. Okay, but on the other hand, in general, what happens? In general, this whatever regions are there, right? All these regions, here people live. Okay, so that means not only in North and South Pole, but all these points we have. So these all points is like different states. So we are having multiple states to live in. So this, if we are having this kind of world, then that is the quantum part. So I hope this analogy also can explain you, and then further definitely in the next lecture I will be explaining you the states even better. So that was the difference between classical and quantum bits. Now next, let us understand that physically what it means. This, whatever I explained you, this linear combination is a mathematical thing that we are going to understand in the next lecture. Okay. And overall, in words I explained that here two possible states are there and here multiple states are there and whatever. Okay. So that is, this everything is a mathematical definition and discussion. But then when I'm talking about physically, like physically one computer I'm going to have, right? We are going to have hardware. So how that hardware will get implemented? What is that? Okay, so that is the question. So physically, actually, there are multiple ways to implement a qubit. Multiple ways are there, okay? Some examples if I can give you. So they are like, the first example is like trapped ion qubits. Okay, so what is this? This is one way of implementing qubits. Implementing qubits means what? End of the day, what did I explain in the previous lecture is, qubits are what? Qubit is a mathematical, object you can say. And physically what objects are available with us? Physically we have quantums. Right? Now, what is a quantum? That also I explained. It is the fundamental unit of a phenomena. Phenomena like light, energy, etc. Right? So quantum is fundamental unit of a phenomena. So that means physically we have quantums. So qubit is a mathematical entity and quantum is something that actually physically exists in our world. So this is the physical entity. Okay. Now physically we have different types of quantums. Quantum is the fundamental unit of a phenomena, right? So if I take light, for light there is a different quantum. For light, what is the smallest particle which is discrete in nature? So that is photons. That is photons, right? Similarly, we have, let us say electricity is there. Okay, so electrons also are considered as quantums because they are again fundamental unit. Okay, so like this. So photon is a different quantum and electron is a different quantum. So both we can use for implementing, let us say, qubits. Okay, so it is like this. So trapped ion qubits is one type how we can implement qubits. So here what are the quantums? Here what are the actual particles that are used? That is a question now, right? So for trapped ions, we use certain elements actually. Like for example, we use beryllium. Okay, or also we have strontium. So these are certain elements that we use for implementing qubits, and they are known as trapped ions because this is one way of implementing the qubits. Okay, about trapped ion exactly I'm not getting into detail because that is a different discussion. Maybe we can have in some upcoming lectures, or maybe not as such required, because too much in the hardware part of quantum computing I'm not going as of now. This is just an introduction. Okay, so this is one way. Another way can be photonic qubits. Okay, photonic qubits. So what happens in photonic qubits? We use photons here. As I told you, photon is a quantum. So if I'm using photons as quantum, then those qubits are known as photonic qubit. So we are using photons. Right? So physically this is what it means. That various types of quantums we have in the real physical world. Out of that, some quantum we can select to implement it for the qubits. Okay. Now one more important question is there, that what kind of quantums can be used to implement qubits, right? Again, this is one important question. We are having various types of quantums, but is it that every type of quantum we can use, or is it that some special type of quantums we can use for implementing qubit? If yes, then what should be the speciality, right? What is that feature that we will look for, right? So the answer for this is that we are going to use that quantum that is having that has two distinct states. This is the criteria that we have to keep in mind. Okay, so various quantums are there, but which ones we can use for implementing qubits? Only those that has two distinct states, or we can perform some action on that so that it gets into two different states. Okay, and why two different states are required? Because as I told you, we need 0 and 1, because these two basis states we have in the quantum. So that is why two different states are required, and rest whatever states will be there, that will be linear combination of this which we will be making. Okay. So that is it. Like for example, as I told here, that photonic qubits are implemented using photons, right? So why photon is eligible? Why we can use photons? What is that property? So because when we polarize photons, when we polarize them, so after polarizing, or we can say that photons can be polarized. Let me write it this way. Photons can be polarized either horizontally or vertically. Either horizontally or vertically. Okay, definitely about polarization and all I'm not going to explain right now. If you're interested, you can study, but again, if you're not too much interested in the hardware part, it will not be required for the upcoming lectures. It is just for the interest and the knowledge that at physical level what is happening. Okay, so if we just keep this much in mind, this is fine. Okay, so what is happening? Photons are there. Why photons we can use as qubits? Because it is having two distinct states. How it has two distinct states? Because when we polarize photons, it gets polarized either horizontally or vertically. So these are two possible states, right? And these two we will be using at 0 and 1. It depends now on the implementation, that which one we can consider as 0, which one as 1. Okay, so that is not a big matter, but two distinct states we are getting. So similarly, even for trapped ion qubits and all, if you go, so here also we get two distinct states which can be considered as the two basis states. Okay. So this was all about qubits, and in the next lecture I will be discussing about the linear combination. Okay. And this linear combination is becoming possible due to some principle. That principle is coming from quantum mechanics. I told in the previous lecture, right, that we are going to use principles of quantum mechanics which has been utilized here in quantum computing. So if I'm able to perform linear combination, then this is because of some principle. So about that principle also I will be discussing. Just that I am mentioning here the principle name is superposition. Superposition. So if I can combine these states and make some new states, that is because of the principle known as superposition. So what is it and how it is done? We will be seeing that in the next lecture. So thank you for today.